Hello, 8th grade. Welcome to Chapter 2. We're going to cover Section A today. Make sure you have your books. Make sure you're following along. Kind of a lot of vocab. Pause as you need to. Write things down. But definitely follow along in your books as we go. Okay? So we're talking about matter. Matter is anything that occupies space and has mass. You guys have mass and occupy space, therefore you matter. Gotcha. But really, matter is something that's been discussed for centuries. Philosophers back in the 6th century BC, before Christ, argued about what it meant, what things were made up of. Democritus, this really old dude, he believed that all matter was made up of invisible particles with absolutely nothing in between them. He's the first one that came up with the idea of atoms, these little tiny invisible particles. But Aristotle believed that there was stuff between them. Okay, so Democritus thought that there was nothing between them, like these voids. Aristotle thought that yes, there was these little tiny things, but there was no empty spaces. Okay, so they kind of had this argument a long time ago. Neither was able to be observed, and so the argument continued for centuries. Okay. As we got more advanced, as we were able to study more and collect more evidence, different ideas kept coming up. So we got this law of definite proportions back in the 1700s. And that's the idea that compounds have constant ratios. So like H2O, what that means is 2 pieces of hydrogen for 1 piece of oxygen. That's a ratio, and that is constant. Okay, so they were true by coming up with this idea. But then the before and after reactions kind of goes deeper than that. And we'll talk about the law of conservation of matter. We'll talk about balancing equations. We'll talk about a lot of that stuff. But basically, what you start with in a chemical reaction, even though it might be different, the amounts have to be the same. Those ratios are still constant, okay? In the 1800s, this idea of Brownian motion was developed. And it's this idea that the particles are constantly moving. And it came off of observations of plant spores. And it kind of looks like this. So let's watch this little video here. There we go. Anytime. There we go. So even if you can't see the particles, they are moving, okay? The air around us is moving. The matter that makes us up is moving to a certain extent. There's a lot of vibration to it. And that was able to be observed back in the 1700s, okay? Diffusion is also a part of this. This was something that was also observed. And it's just this idea that particles will move from a high concentration to an area of low concentration. You can see this happening in an enclosed space. If you spray air freshener in one part of the room, it will eventually diffuse throughout the room, okay? And so it's evenly spaced all throughout it. That's the idea of diffusion. All right. Eventually, we came up with this particle model of matter. This is in the 1900s, and there was enough evidence to say, yes, that all matter is made up of these tiny particles, and they are in constant motion, okay? And those particles are known as atoms and molecules, okay? So an atom is basically the smallest piece of recognizable matter. An atom can be broken into smaller parts, but if we're talking about matter, it's made up of all the elements on the periodic table. A single atom of one of those elements is the smallest piece of identifiable matter you can have, okay? Again, it can be broken into its parts, but then it's no longer that element, okay? If you take some atoms and you stick them together, then you get a molecule, okay? So let me get my pen here. Got it, okay. So this is a single atom. If you put several of them together, so each of these little circles you see are atoms. So the white would be one element, the blue is another element, the red and the black are different elements, and so on. You stick them all together, even though it's several atoms, that's now a different substance. A molecule is the smallest piece of a compound. We'll get to that, okay? So how do we measure matter? Because it can be really small amounts or it can be really large amounts. So we've got these different measurements. We talk about weight and mass, and they're 2 different things. We use them interchangeably here on Earth because they don't change because we're always staying on Earth. And this is what I mean by that. So weight is a measurement of gravity. It's the force of gravity pulling down on something. So when you stand on a scale, you are being pulled down onto that scale towards the center of the Earth. That's gravity. It's typically scientifically measured in newtons. We refer to it in pounds, but it's still a measure of gravity. That will change depending on where you are. If you go to the moon or Mars or somewhere with less gravity, your weight will actually be less. If you put a scale on the bottom of a swimming pool and stand on that scale, you will weigh less because the buoyant force of the water decreases the effect of gravity, okay? So your weight can change depending on gravity. Your mass, on the other hand, is just the amount of matter in an object or in you. That doesn't change. Your mass, your overall total matter isn't going to change depending on the gravity, okay? We measure that in grams and kilograms and things like that. Volume is the amount of space something takes up. Remember, in order for something to be considered matter, it has to take up space and it has to have mass. Those two things are what we look at to consider something matter, and everything around us is made up of matter. So the capacity of something, the volume of something, it's measured in liters or kiloliters or milliliters in the metric system. And then we put those two together in a formula to measure density, and that's the mass of something in a given amount of space. Okay, so I've got two blocks here. They are both the exact same size, so these substances are taking up the exact same amount of space. Their volume is the same, but one is definitely heavier than the other. And the only way I can demonstrate this to you is by sound. So I'm going to drop this one on the counter and listen. It just makes a small sound. Okay, it's a little wood block. Now this one, I think this is brass, I'll drop on the counter. And I'm dropping them from the same height, like an inch. There's the wood, there's the brass. The only thing that can be different is the mass, okay? This one's much heavier, which means it's much denser. There's more matter shoved into this little cube than there is in this one. That's why it's heavier. This one is more dense, okay? We'll talk a lot more about density in a later chapter, okay? The formula is mass divided by volume. So I want you to turn to page 29 in your books right now, and let's look at example 2-1 together, okay? And that problem says that you have a sample of aluminum. This is aluminum. It's not as heavy as the brass, but it is heavier. It's denser than the wood. Anyway, a sample of aluminum has a volume of 14.8 milliliters and a mass of 39.96 grams. What is the density of aluminum? Okay, so you're going to plug in what you know. This is the formula. This is always the formula, okay? I know the mass is 39.96 grams, and I know the volume is 14.8 milliliters because it told me that, okay? So I'm plugging those in. Again, there's the mass, there's the volume. I'm going to divide those two amounts, okay? Mass is divided by volume, so 39.96 grams divided by 14.8 milliliters gives me 2.70 grams per milliliter. So when you plug the numbers into a calculator, you get this 2.70, okay? Grams and milliliters can't be divided. They don't go away, and so we keep them in that fraction form that kind of follows along the formula there. So that's the label for density, is grams per milliliters, or whatever measurement of mass you were given and whatever measurement of volume you were given. And so you would label it with those measurements, okay? And that would be example 2-1. And that is the end of our lecture.